Electrons that could not move through a solid become free and mobile. In the simplest way, an electron can absorb a photon that has enough energy to liberate the electron from its binding potential. And things get more interesting, more complicated if a light wave has no photons with such a high energy. In this case, an electron has to absorb more than one photon at once to become free, or an electron can also tunnel through a potential barrier, and this way it can become a freely moving particle. Many things. We are particularly interested in studying the dynamics of photoinjection, finding out how quickly it happens, how to confine it to a possibly short time interval, and also in studying how a medium acquires its new optical and electric properties after photoinjection. There's also some interesting many-body physics associated with that, because electrons and holes in a solid are quasiparticles. The properties of these quasiparticles depend on how they interact with their environments. And when many charge carriers appear at once, it takes some time for those interactions to build up. When many charge carriers are photoinjected by a very short, very intense laser pulse, the conductivity of a medium can increase by many orders of magnitude within an extremely short time interval, as short as a few femtoseconds. And we wanted to know how exactly it happens, how quickly the conductivity increases, what dynamics are essential there, how to understand these processes. I didn't do experiments myself, I'm a theorist, but I can quickly summarize what my colleagues experimentalists did in the lab. They did what is called pump probe measurements, which means that there was a pump pulse that photoinjected charge carriers and a probe pulse that tested how they move, tested the optical and electric properties of the medium. And both these pulses were transmitted through a very thin film of a solid. In particular, we use silicon dioxide and silicon. And what makes these pump probe measurements special is that we recorded the time-dependent electric field of the probe pulse, or we recorded the changes that this field experienced as a result of photoinjection. We did so for a range of delays, and this was a big experimental feat. Well, to do what we did, and this is the optical field sampling, measuring the time-dependent electric fields, is challenging by itself. But in addition to that, we had to get possibly direct insight into the motion of charge carriers in a solid. And this is only possible if one uses very, very thin samples, so that various propagation effects do not play a big role. However, using a thin sample means that you have to measure very, very small distortions of your probe pulse. And to measure such small distortions, one needs a technique that combines the large bandwidth necessary for optical field sampling with a very high sensitivity and a large dynamic range that are necessary to measure small changes in the time-dependent electric fields. And even with such a technique, which we developed ourselves, measurements would typically take many hours, during which the pump and probe pulses would change a bit. So we had to find a way to do the measurements and analyze their results in a possibly robust way. Well, they were twofold. First of all, this was one of the first demonstrations of pump probe field resolved measurements, optical field resolved measurements, which is, I think, a big step forward. We found out how to make it work, and now other scientists can use our insights to do similar measurements and answer their questions. And on the other hand, we did learn something new about the light-driven motion of charge carriers after ultra-fast photoinjection, and we were able to develop a simple model that describes how the conductivity of a solid evolves in time during the first couple of femtoseconds after photoinjection, and we were able to explain our measurements with this model. Well, let's say all modern electronics is based on our ability to quickly increase and decrease the flow of charge carriers through electric circuits. And our research is about studying the ultimate speed limits of this control. The insights it produces might eventually lead to the development of new technologies that would enable petahertz scale signal processing, although I would argue that this is a long way to go. In the foreseeable future, I'm thinking about new methods for ultra-fast attosecond scale metrology.